In the last chapter, I showed you a bit about visualization of fluid flows, and I explained you it's really difficult to make a good visualization of fluid flow because many fluids are invisible, like air or water. They're transparent. It's difficult to visualize the flow, and so we will also use mathematical description of fluid flow, for example with computational fluid dynamics, but also with methods from the theory. And what can we use? For example, if we have geometry and you can imagine the fluid flow, it's turbulent, you have a swirl, it's really difficult to describe this in mathematics. Yeah? Because it goes in 3 dimensions in space and not only into 1 dimension. But what we can do, we can try to make our problem, our geometry a bit more easy. For example, if you have flow around a bullet from a cannon or from a pistol or a gun, we can try to make it easier. Yeah? We can prevent 3-dimensional coordinate systems and try to make easier descriptions. Or if we have fluid flow around a long cylinder, around a long tube, we can make it a bit more easy. We can just make 2-dimensional simulation. Or if we have fluid flow around a car, we can make it easier. So, also, from time to time, I want to give you also impression about innovation, about what we can do with fluid dynamic tools. And a really good example is the development of airplanes. Yeah? We have a lot of different airplane types, and even through the last century there was a lot of invention with these airplane types, and even nowadays that's computer visualization of some students from the University of Delft, and it's a new concept about optimized, a better airplane, and that's something I want to show you, that we don't have to use the same airplanes till the end. We can try to make better geometries, better innovations here. How can we do it? How can we examine the geometries? Here we have a geometry of a jet, of a military jet, and it's a model, but we can also use some small smoke sources where we produce some smoke in different colors, here red color, blue color, green color. And now if we go to the wind tunnel, we can examine the geometry and we can optimize the geometry here. But it's much easier if we do it with computers, with computational fluid dynamics. Here we have, first we have to build a model, we have to construct a 3-dimensional model, and then we can examine the fluid flow around the model and the pressure fields on the outer surface of the model. And of course the forces, lift force and drag force. And then, if you have our optimum geometry, nowadays it's really easy. We construct it in the computer, we make a computer model, and if we optimize the model, if we have a better geometry, then we just go to our 3D printer here, we print it, and then we can make experimental examinations. Yeah, that's me in a master class of students. Here we do computational fluid dynamics, and then we want to build models here of an airplane or of other objects, and then we want to optimize it. But today we are not in the classroom here, we are at home, so yeah, we also should do the same exercise. We should download the software on our own, and you should learn it from the videos. Yeah, if you learn it, I hope at the end of the semester we can also make some experimental examinations in the wind tunnel, and if we have printed the airplanes, let's see if we can finish it. But if we have it, we can work a bit on it, and then we can produce our airplanes, we can print them, and go to the wind lab and make some experiments about it, test the wind velocities, and so we get new ideas about new projects, about new innovations. And let me say, fluid flow, it's something that is invisible, you cannot see it, you can't really realize it, but fluid flow is a big driver for innovation. Many new products, many new vehicles, or many new inventions or innovations will be made by examination of fluid flow problems.